Okay, hi. Sorry about that. Uh, if you did not already, please tell me what's the best TED Talk you have seen for the attendance today, or something like that. And I would like to show you the final exam schedule for this semester. So our class happens at 4 o'clock on Tuesday, Thursday. That means our final exam is Thursday, May 6th at 2 o'clock p.m. So that is what I have included on the As You Learn page. In the final exam details section. That font's kind of small. Okay, so you don't have to go to that special calendar. You can just go to the As You Learn page to see when our final is. And it's going to cover the second half of the semester, mostly, but we can't avoid some stuff from the first half of the semester, just because it's part of the calculations for the second half. But we're not going to focus on the stuff from the first half of the semester. She broke an egg. It was very devastating. Okay, sorry about that. So, like I said, we were going to focus on the second half of the semester, so that's chapters 6 through 12 on the final exam. And it will be similar, the problems will be similar in length to those problems that were on the midterm. But we're going to have a lot more time for the final. We get 2.5 hours for the final. So there will be more problems, but similar problems. And if you cannot find a way to use Python for curve fitting and plotting on May 6th from 2 to 4:30, please let me know, and I will help you find a way. But that's going to be required on the final. And I will ask you to show certain calculations that I need you to show, and if you don't have, and you don't have to show them if I don't ask. Like, you know, the calculation of the entire standard deviation, for example. Probably I won't ask you to show that for every single time. You have to find standard deviation. Questions about the final? Okay, so this is not really a featured concept in your book, weighted linear least squares regression, but it is pretty important for your scientific career and definitely for senior seminar. So I want to spend some time on weighted linear least squares regression. When you're in senior seminar, capstone course, Physics 4210, someone will probably ask you, is that a weighted fit? And they're asking, is that a weighted linear least squares regression? So I want you to be able to answer that question. So we're going to go to your book, page 201 in your Taylor textbook. The error analysis book. And number 9 in chapter 8, this is a homework problem. It's about weighted least squares. And this is the only place this shows up in this book, the weighted part. And what's different here is that the uncertainties, we know that y values have big uncertainties compared to x values, because that's like a requirement of linear least squares regression, a required assumption. But now we can consider what are those uncertainties in the y values as part of our fit. That's what we're doing in weighted least squares fitting. So now we're taking our uncertainty values for each y value. We have a corresponding, for each y value y sub I, we have a corresponding uncertainty sigma sub I. That is, they're calling it sigma here, but it could be, you can use whatever symbol. It's the uncertainty in y. Okay, so each y has a corresponding uncertainty that, shows that y error bar. And now that quantity, that error bar size, is part of the calculation. If it's a big uncertainty, it counts less towards the fit. If it's a really small uncertainty, it counts more towards the fit. So that means points with better precision count more, are causing that fit to be kind of gravitating towards those points instead of other points that have big uncertainty. So I'm going to show you an example. Basically, we now have this, what's different is we have this weighting value. The calculations and whatnot are pretty similar to ordinary linear least squares regression. For weighted linear least squares, we now have this w sub I that's equal to 1 over sigma sub I squared. So it's the inverse of the uncertainty, this w sub I. So the bigger the uncertainty, the smaller the w, the less weight that point has. And the smaller the sigma value, the smaller the uncertainty, the bigger the weight, and the more that point is going to affect the fit and affect the calculation of the slope and the y-intercept. So we have this quantity delta, which we basically had before, but now it has these w's included, w sub I, which also show up now in the b and a calculations as well in the numerator. So this is real similar to linear least squares that we've already done. This is regular linear least squares, ordinary linear least squares. There's no weights here. There's no uncertainties included here. This is just, there's points and there's a fit. And that's it. Slope and y-intercept. So when we create this line of best fit, what we're actually doing is finding the best y-intercept and finding the best slope. And we do that via this linear algebra technique that we learned. And then we have these uncertainties for A and B, but none of this was ever, these uncertainties never depended on any other uncertainties before. This was just based on the plotting and not any kind of measurement uncertainty. So now with linear least squares, weighted linear least squares, we're including these uncertainties in the y value, which basically come from the measurement uncertainties that went into the calculation to find y. Or maybe we actually measured it, and that's an actual uncertainty of a measurement. But now we can connect, we have the opportunity now with weighted linear least squares to take our original measurement uncertainties, like from my ruler, from my meter stick, and my timing apparatus, whatever I'm measuring with, my calipers, those uncertainties for those instruments are now going to go into the calculations and be a part of the uncertainties that we find for A and B. So it's a nice way to see that effect of the measured uncertainties. Okay. We are going to go back to, sorry. The Python tutorial. I'm not sure we've ever actually looked at this Python tutorial. It's on the As You Learn page. At the, like in this week. Go too far? Yes. Okay, here we are. Week 11, where we're supposed to be talking about covariance and correlation, but I'm talking a little bit more about weighted linear least squares, or about linear least squares in the sense of weighted linear least squares, because I think it's really important. Here is the link I want to direct you to. There's a lot of information here. We don't need to go through all of it today, but there is a tutorial on how to create your own function for weighted linear least squares. And also a very nice kind of mathematical framework for calculating weighted linear least squares, nicer than what's in your textbook. So here you can see the theory in a little more detail of everything I just went through that was on that page in the textbook. And below that, we have a tutorial on how to write code to solve for A and B, and then the uncertainty in A and uncertainty in B with weighted linear least squares regression. Excuse me. Okay, so here's the section with the code, and it spells out everything you need to create your own function that's going to carry out weighted linear least squares regression and calculate those uncertainties that correspond to the A and B values. I'm going to show you some examples of that as well that I did in Python. So there is some extraneous information here. There's a few different ways that the author has shown to kind of print or report the final values. So there's a few different ways to do that here. One is through just printing them, and another way is through a function. You know, lots of different ways to do that. And then there's a section about plotting, which we've already learned about, but now we can include error bars in our plot. So there is a example here of including error bars in the plot. And then there's also a weighted linear least squares regression with some example data points that they generated on their own. I did kind of the same thing, so I'm going to step through mine really slowly to show you the steps to get to this point. So up to this point, by the way, we have done like a quick version of linear least squares regression in Python, which was just a built-in function. But now we can, now I'm going to show you an example of writing your own code to achieve that fit. Okay, do we have questions? All right, I've got Python here ready to go. And I have some data here that I can't remember where I got it from. Some homework problem or something. I think maybe it was medical physics. I don't know. We have some measurement of intensity happening of light or something at different lengths or distances from some 0 point. So we have read this in via an Excel file, and that Excel file is something I've preloaded into this database or whatever this is called. I just dragged and dropped that Excel file into this window frame, and then it was something that the Python program could find by using this pd.readExcel. And that's using an imported package that's helpful for importing and exporting data. So I read in the data, which is called Python data. Read that in here, have that in quotes. And I'm reading an Excel file. It automatically reads in also the title in my column of my Excel file for both of the tops of the columns. And then it puts in these numbers for me of like the row number. So in my Excel file just looks like intensity versus thickness, or it just has these two columns with intensity and thickness at the very top in the cells at the very top. Okay. So then I read in a bunch more libraries. Sorry. Go that far down. Reading in a bunch more libraries for plotting, for doing math, for curve fitting, etc. And then, right, this keeps moving more than I'm expecting. Then I do a bunch of setting up the plot formatting, like what font to use and how big should it be, and etc. What kind of different fonts for different parts of the plot. And notice that I've put these in different lines. You can put, your code in to one cell here. You can put lots of lines into one cell, or you can do one line at a time. I may have mentioned this before, but it's nice to be able to do one line at a time because you can debug a little easier. You can see which line of code is screwing up if there's a problem. But either way is really fine. Okay, so after setting up importing the libraries, setting up the formatting for the plot, I just plot the data here below. Okay, so I read in the data into a variable here, x column, and I read that in by using the Excel data that I read in earlier. So earlier I created this other variable, Excel data, and read that data into that variable. And then I wrote this to print to make sure it looked right. So I wrote Excel data and then printed the data to see how it looked. And now that's like a variable with that data in it. I can do Excel data.thickness, and it automatically takes that word at the top of the Excel column and will call that the name of the column. So I can read that column into X column, read that data from the thickness column into this variable X column. And then I do the same thing for the intensity column. I read that into Y data. And then I plot the figure and add some more details as far as formatting. We put in the data with this command. We put in a title with this one, and we add some X label and Y label text, also with units. And then we put in how large our font size should be for the tick marks. So a lot more formatting. Okay, after that all runs, we get this plot. I'm going to zoom out a little here. Okay, let's see if we can fit the code into the window. Okay, it's pretty close. So remember, I've got X column for my X data, Y column for my Y data. I am plotting that data in just a scatter plot here, just to see how it looks. So there it is. I've got my labels and my title, and my data points are taking up the plot, in a complete way. So it looks pretty good. So at this point, this looked really clean to me, so I wanted to add some noise to this to make the fit a little more extreme. So I just used this np.random command to create like random numbers, basically. And then I called that Y noise, like a whole bunch of random numbers. And I added the random numbers to the old Y values here. And then I made up some error values. I said X error. I made up this variable X error and called it 0.01. Or set that number to be 0.01 for the entire array for all of my X data points. And then for my Y values, I put in particular values of error for each data point here. So I made up arbitrary values where I have a whole lot of like big values for low X values and then small Y values for larger X values. And we're going to flip that around to see how it changes the fit. Okay, so I printed Y just to see how it looked. Now I've added my old Y values with some random numbers. And so I have this new list of numbers here. And then I wanted to plot that to see how that looks. So I used the same commands to have a different title. Everything else is the same. So here's my plot from before, but I've added some noise, some randomness to the numbers here. They're a little more, far away from the eventual curve. Okay, so, and again, the point there was just to make this kind of more extreme because it looked so linear before. So I was trying to make it look less perfect for the fitting. All right, so now I want to plot my data with my error bars showing. So I go back and I went back and copied and pasted the plotting command from earlier to plot the scatter plot. And I included this plot error bar command where you can include a lot of formatting for your error bars. And if you you'll notice that you're indicating the X data values, the Y data values, the X error values, and the Y error values there. And then this is what it looks like for the noisy data that I made noisy on purpose, and then I added error bars that were on purpose much bigger on the left-hand side than compared to the right. And I did that because I wanted to show if I do a weighted fit for this data with these error bars, that means these points should have a lot more weight. And the fit should be much more focused on these data points. And these data points should not be so important. They, it's not going to be as important for them to like be really close to the line of best fit. So that's what I tested out with my weighted linear least squares code here. Okay, so first I just renamed my X values X because that's what was already written in the code that was given in the tutorial. So I just copied and pasted the code from the tutorial here and changed, renamed my X vector to be x, so I didn't have to go back here and change everything to x column. And then I'm basically defining a function here in Python. This is how you define a function. You say def, you give it a name, and you say what the input variables are going to be. And then you can create this results return variable to give you back what you need to know, which is the a value, that's the y-intercept, the b value, the slope, the uncertainty in a, the uncertainty in b, and then chi-squared, which we haven't talked about yet, but we're getting there in the book. Chi-squared is basically I forgot the symbol we used before for it, but it's the square root of the sum of the squares of the distances, the residuals, the distances of each point from the curve. Okay, so after creating the function, then the function is called here and computes the code that is shown there above. So basically calculating a and b with this weighted linear least squares regression technique, where now we are including this w quantity as part of the calculation, or the uncertainty quantity as part of the calculation. So I just went with the easiest output method, where it just prints the numbers out. You can do this different ways, where it puts it in a variable for you or something, and then you can like use that variable in the code. I just took this and like typed it in here. So I was kind of lazy, but it works. So I took the slope that was printed by my function. By the way, I did copy and paste this too, but it's the point of this print here is to give us back that value of the slope and the value of the y-intercept. And we're putting in artificially, you know, these labels that are going to tell us that's the slope, that's the intercept. And that's the error in the slope and the error in the intercept. Okay, so I took this number, minus 25.798, and I put several digits of that here. That's the slope of my fit line. And then I took the y-intercept that was given, there it is, and I just typed in that number here, 108.092711, like up to several digits. First, also, I'm creating a bunch of x values, a whole bunch of arbitrary x values in the range of my fit. So let's go back up and check that. We have 0 is the minimum, 1.5 is the maximum. So that's like, I want to make a whole bunch of x values for my fit so I can plot my fit. I can't just use a function. I have to build a line with a whole bunch of data points and then plot that. And that's my line of best fit. Okay, so sorry, internet not being my friend today. Can y'all hear me? Okay, so let's get back to this excitement of weighted linear least squares regression. I think I was talking about creating a whole bunch of x values to plot my fit. So I start at 0, that's the minimum. I want to go up to 1.5, that was the max along the axis of the fit. And I made an arbitrary 100 data points from 0 to 1.5. And then I'm going to create a whole bunch of, or 100 corresponding y values to plot. So I multiply the slope times the x values plus the y-intercept, and that's my y values. And then I still have all the same code from before, where I'm plotting. I have font sizes determined and different labels being defined and error bars being included. And now we are also plotting on top of the data values. We're still plotting the scatter points, the X column, Y column like before. And now we're also plotting X function and Y function, the 100 points that are my fit. And I copied and pasted this text here from above to say what the label is for the fit line. So nothing fancy there, just copied and pasted it down. I'm sure there's awesome ways for you to do that with some kind of variable, which I encourage. But I'm just getting it to work to show you how to make it work. So I just typed it in. So this is what it looks like. So did it work? Did what I say happen? Yeah. Thank you. So yeah, we have big uncertainty here. This should not have much weight. These should have less weight, these points. These have much smaller uncertainty, and they should have more weight, which they do. The line it goes through them much more than it goes through these, like the middle of these data points. The middle of them is like here. It doesn't go through the middle of them, but it goes through the middle of these, the ones that have a small uncertainty with a big weight. What if we go and change the uncertainties? What if we put small uncertainties over here and big uncertainties over here? I know you're dying to know, so I went and did it. Scroll up all the way. Okay. So I copied my original program here. I should say I right-clicked it and duplicated and gave it another name like sub B when you're, yeah, got a sub B here, whatever. So we have another file here where I'm just going to change I do all the same things where I have the data and I make it noisy. And now I'm putting in ridiculously large error bars on this end of the plot and really small error bars on this end of the plot. So now we should have much more weight coming from these data points and much less weight coming from these data points. Our line should not be going through here so perfectly anymore like it was before. Perfectly, well, not perfectly, but very much through this cluster of points. And so I should expect the line to be not through this cluster of points anymore, but more kind of focused on these up here. So I do everything the same, and we do get better agreement from our fit with the higher weighted points. And this is no longer going really through the center of these like it was before. It was kind of like this before. So I did have to go back in, and after I did this calculation, a new slope, a new y-intercept happened because of the weighting being different. And so I created a y function this time based on that quantity of slope and y-intercept, those quantities of slope and y-intercept. So I took these and literally typed these in here, and then also typed them back in here to make my function here consistently correct with what I'm doing. Okay, so that is weighted linear least squares regression, and you're going to be expected to do this in senior seminar. So that's why I'm covering it now. Even though we're not really going to focus on it a whole lot in this class, I want you to know how to do it and where it comes from and what it is. So when you get to senior seminar, you're ready. Or, you know, in life as a scientist also. So do we have questions about weighted linear least squares or Python stuff? If you If I went too fast or something with the Python code, I'm happy to go back and show some of that. No questions. Maybe we have a question in the chat. Will this be on As You Learn? Yes, this, I will print this to PDF because I tried to save it as like a Python file and upload that, and that didn't work out. So I'm going to print this to PDF, put it on the As You Learn page. I'll put both of these, the two different examples with the two different sets of uncertainties. Yeah, I'll put that on As You Learn. Thank you for asking. Other questions? Okay. Great. So we will move on to actually talking about correlation and covariance like we're supposed to this week. The As You Learn page was a lie, almost, except for this 10 minutes that I'm covering now. This is what I'm talking about. It didn't really dominate week 11 like I was hoping. But that's okay. We needed to talk about linear least squares regression in detail. All right, so I just want to cover like kind of what is the concept of correlation and covariance. So before we even look at this, let me get some, what are your ideas on what does covariance mean and what does correlation mean?
Are you asking us like kind of like what we think it means?
Yeah. Yeah. I mean, correlation is a word that's, you know, in more than math and physics, but it has a similar meaning and a specific
I think correlation has something to do with how closely, how much the data points relate to each other. Like if it has no correlation, then they don't relate to each other.
Okay, yes. What about covariance?
It looks like it means like how well the data fits.
Okay. Which is kind of similar to correlation. If you have a really good correlation, you're going to have a good fit too. Yeah, but that is true. Anybody else? Maybe y'all learned this before in statistics class. Okay, so yes, Ethan, you were right. Like, what if we have a whole bunch of random data? Maybe not random data. We have a whole bunch of data, and we're trying to take two variables and see if one depends on the other in any way. And I think what Ethan was saying was, are they related to each other? So that's another way to say it. Yeah, are they related to each other? Is there a dependence of some sort on one, like a linear dependence, quadratic, whatever, some kind of dependence? Is there a dependence at all? If there isn't, then that's like there's no correlation. And if there is a very strong dependence, then there is a high correlation. So that's still related to how good of a fit you're going to get, but it's a separate concept. And then covariance is also related to how good a fit is going to be, like Allison was saying. But it's going to also be related to how well the data fits the model in the first place. Okay, so let's get to the physics instead, or the math, I guess. So as before, we want to determine a value Q. calculated value Q that comes from measured values X and Y. Okay, if we, sorry about that, we take n measurements of X and Y. So we have a whole bunch of X sub i's and a whole bunch of Y sub i's. We have n of them. And we're going to take our X sub i's and our Y sub i's and substitute those into some mathematical equation, some mathematical model, and we're going to calculate Q. So we have been doing a whole lot of linear regression. We could do that here, but in this case, we're going to talk about doing in like an averaging sort of approach in order to determine the best value of Q. So not considering a fit right now, we're going to take the average of our X values and Y values and use the averages to calculate the average of Q. So we're going to take all our X sub i's and average them and get X average. And we're going to take our Y sub i's and average them and we get Y average. We substitute those two quantities into Q and calculate Q. And that's Q mean, Q average, Q bar. Okay. So we also are going to find a standard deviation for Q, but in terms of standard deviation squared, it's going to be 1 over the number of points, and we're going to multiply that by the sum of the individual Q's from the individual X sub i's and Y sub i's, and we're going to subtract the mean Q from each of those individual Q values. And we're going to square that difference and add them all up, and then divide by n. Okay. If we assume those uncertainties in X sub I and Y sub I are small, our original measurement uncertainties, if those are small and random, then we can approximate, if they're truly random, we can approximate the X sub I error as one value, a mean value. And then also the same for the Y. I think I said that wrong. I'm sorry. We can approximate for the X sub I values a mean value of X, and we can approximate for the Y sub I values a mean value of Y. Now, to make things easy for ourselves, we're going to do a Taylor expansion of our Q. Q, remember, is the quantity that we are calculating with our mathematical model by plugging in our measured values of X for X and Y. We're going to do a Taylor series expansion of Q about our X bar and Y bar values, these average values of X and Y. Okay, so this is valid because a Taylor expansion is used when the differences between all the values around which you expand are small, which is the case. We already said that was happening up here at the top of the slide. So as a reminder, here's your Taylor series at the bottom. And we're going to be expanding around X and Y. Okay, since it's a function of two variables, we are just going to keep the first order terms so it doesn't get too crazy. We don't want a whole lot of terms. And we know with the Taylor expansion anyway, these high order terms don't really matter. They are so small compared to the low order terms that we can just leave them off anyway. Okay, so we are using that Taylor expansion. We are going to take the F sub A quantity and the df dx x minus a quantity for x and then also for y. So we're going to take the derivative and for that second term with respect to x and also with respect to y, and add that to the first term, which is a function of x and y. Now we have a quantity for q sub I that we can substitute into our variance equation from earlier. That's basically our, like a measure of our uncertainty, of our error for our calculation of q when we are doing it this way. Okay, what we're going to find is we are about to define the covariance at the end of this derivation, which is a measure of the difference from each x quantity and the mean of the x's, and then the y quantity and the mean of the y's. We will have to stop now, and I will show you how to get from where we left off to that final point next time. And I hope you have a good weekend. Please let me know if you have any questions. I'll stick around.